Good morning, everyone. It's really great to be here. So I'm Dorrit Hammerling. I'm, like John said, an associate professor in statistics and data science. But before that, I worked at the National Center for Atmospheric Research in the Statistics and Machine Learning group. So for about 10 years, so I spent a lot of my time thinking how to make sense of large data with things that are related to things we measure in the atmosphere. On that note, I'm going to talk about monitoring methane emissions on oil and gas facilities. And if you have listened to the news lately, you're probably aware of the Inflation Reduction Act that some people also refer to as the climate bill. And if you work in oil and gas, I'm sure you're keenly aware of what that means for monitoring methane emissions and reducing them. There will be a lot more regulation around it. So very quickly here, what is methane and why do we care about it? So what you see here on the right-hand side is a gas stove. You might have one at home. I'm sure you have used one in a friend's house. And as the name implies, gas stove is powered by natural gas. And the main component of natural gas is methane. And if you live in the United States, that methane is, or that natural gas is likely produced in the United States and brought to your house via a line of pipelines and all kinds of facilities on the way. So what we really care about is limiting emissions that could happen anywhere along this line here. And one important fact to know about methane, you can't see it. Well, there's no black smoke coming out. It doesn't have any odor or smell. So that makes it a little bit challenging if you're trying to see, are there any leaks here? And here's an example of a bit more typical facility. So this is a midstream facility, specifically a compressor station. And that's the kind of facility, as you can appreciate, there's a lot of complex things going on. So anywhere on this facility, we could have some leaks. And as I said, we can't see it, we can't smell it. So one saving grace has been the development of sensors. These type of sensors that I will be talking about, so-called point sensors. That means they're placed on the facility and measure methane concentrations in a given location or a given point here. As a sketch here, you can see these blue stars here, and that's where we would have these, would be able to measure the concentrations of methane at that location. What makes that a little tricky is we are only indirectly measuring what we actually care about. So we are getting these methane concentrations at these points, but what you're really interested in is there a leaking piece of equipment, and how much is that piece of equipment leaking? In more technical terms, we refer to these type of problems as inverse problems. And the reason they're called inverse problem is because we have a true process. So here we have a leaking piece of equipment, and then we have wind blowing around or diffusion happening, and we are able, that methane gets transported, and we are measuring these concentrations around the facility. And that's where we have methane concentrations, what we observe at the sensors. But what we do mathematically is we are only getting the data from these sensors, and we are trying to do the same game in inverse. So we are trying to come back and find out what were actually the leak locations and how much is it leaking here. And I'm going to show you a little movie because it's much easier to kind of appreciate why this might be challenging. It's something we want to think about. So let's see here on the right, that red triangle that you see, that's a leaking source of methane at any piece of equipment on a facility, let's say. And these sensors, also these black dots that you see around them, those are the sensors that pick up what are the resulting concentrations are. So what you see here, the reason this is moving is because we are using wind data to transport what actually happens with that leak location here. This is real wind data. So for example, if you look at sensor 1, that one hasn't seen any action yet, but right now it's picking some of it up here. So as you can appreciate here, if you had only looked at sensor 1, you would have never thought there's anything going on that side. So these on the left here, these data that it's building up again here, this is the data we work with mathematically to find out, is there really a red triangle happening? Is there any leak at all? Or is it just ambient background concentration? If there's a leak, where is it and how much is it leaking? So that's what my research group is specialized in. We think a lot about how can we solve this problem. And one aspect in there is, so the way we translate what we see in the concentration space back to what the actual leak is, we use these so-called atmospheric transport models. And there's a whole range of these models you can use. Here on the very right, we see the so-called large eddy simulation models. These are extremely complex models. That's what's used if poisonous gas is released in a war situation. The drawback with these models is there's always a trade-off if you model anything. So these models are very computationally intensive. So they're very precise, but they're very computationally expensive. These kind of models, they might need days to run on a supercomputer. So clearly, if we're in these kind of settings that we're a facility, we're usually trying to figure things out within 15 minutes, half an hour. So we can actually do something about, let the plant, the operation know there is a leak, send a crew out and fix it. So we don't necessarily want models that take a day to run here. On the left-hand side, that static image up there, this is so-called Gaussian plume models. These are very simple models. They just assume the wind is always the same. As you have probably seen in that movie before, that's not always right. Clearly, if we would always assume the wind is the same, we would think sensor 1 should have seen something. So what we are working on is that interface, trying to find out what's the simplest model that we can practically work, but still get the accuracy that we can actually do something about methane emissions. And I'm going to show you one set of initial results we have that we just got that we are rather excited about. So these are results from an experimental testing setup at the so-called METEC facility at Colorado State University. So that's a facility that emulates a production environment, and there are controlled releases. That means we know exactly the truth of how much methane is released. That is a great way to test our algorithms, how well are we actually doing if we have a truth here. So you see that black line here, that's the one-on-one line. If you know anything about stats, that's where you'd like to be. Clearly our data here, we are not quite at the one-on-one line, but you can see we have come a long ways of actually getting some results that really resemble very closely to what's going on. I'll add the caveat here, so that's a very simple facility. So these production facilities, there isn't too much equipment around. As you can imagine, that image I showed before of this midstream compressor station, much more complex, because there we have buildings standing around and we have to worry about turbulence and things like that. But we have come a long ways towards getting closer and closer in solving this problem here. All right. With that, I would like to thank all my research group and the great students who have been working with me on solving this problem. Thank you.